Okay, so of the task that I showed you at the beginning of our session here, a lot of work was done after working meeting 2 and workshop 2, and so we had a lot of additional things to go through that we couldn't all compress into our workshop here. So as a result, we had a larger working meeting on January 28th and 29th, which many of you were at, going over the technical items that were being done. Bob had talked about the response of the GMP developers, and I'm going to go over several other topics that were covered at this meeting. So for those of you who were here, this should be review, and I hope it reminds you of what we discussed. And for the others that weren't at the January 28th, 29 working meeting, this will serve to summarize what was discussed for you. So some of the topics that were covered, we will be going into more detail here in the next few days. So responses from the GMP developers, you already heard from Bob Young. Directivity models, this has now been taken all the way to a model for both strike slip and reverse that Jenny Watson-Lamprey will talk about on Wednesday morning. Visualization of the epistemic uncertainty. So Nico Kuhn will be talking about that this afternoon. We wanted him to get to that before we're all tired, okay, because it's really important that you follow this. This is really the framework, that fundamental framework we're trying to use right now to go forward. And then part of the data for the path effects I will talk about on Wednesday afternoon. So I'm not going to summarize anything that was discussed on those 4 topics right now. So the ones I'm going to summarize for you only are listed here for the Arizona data. This was all the work that was done. These were the peer studies that were going on for these topics. So I'll go over the site condition studies that were done, the ground motion processing, evaluation of the distance scaling into Arizona and the Arizona kappa values. As well, we looked at hanging wall effects, and I'll talk about the validation that was done of the finite fault simulations for smaller magnitudes, and then an interpretation of what that means for the small hanging wall effects at small magnitudes and what we might need to do to our models. And then I'll talk about the shape of the ground motion distribution. And I missed one here, which was the, I don't think it's on another topic. I might say complex ruptures that I'll talk about as well. Okay, so this is going to be fast. So I have 40 minutes to go through just the highlights of these presentations. So Rob Kahn did a study characterizing the shear wave velocity at the selected seismic station sites in Arizona. He looked at 11 sites were characterized here, so using his surface wave inversions to estimate the values. And so the power plant, Palo Verde, is in this region here, and these are about 100 kilometers or so around the power plant. So Rob did his evaluation using several different methods, but it's surface wave testing and several different, I should say, inversion techniques. From these, he gets a velocity profile, and then we're going to summarize that initially here just by the VS30, so the average based on the travel time in the top 30 meters here. This would be a case where it's a soil site, and you can see it's coming down about 500 or 600 meters per second. But what you see as well, the depth of the soil is not identified. That is not reached in this profile, so it's more than 100 meters. So we don't have a good control over the depth of the profile. There's a rock site that came out, so this is the same thing, shear wave velocity here, depth, and now this goes higher, and you're getting up over 1,000 meters per second. Velocities below 10 meters. So now we're seeing a shallow soil over rock. So from all of these, this is trying to find some way to display what they are, but these are the shear wave velocities. This is his estimation of covariance of the estimate. but just use this to think about how these are spread out. There are 2 sites that they characterize that are rock sites, higher velocities. The rest are soil sites. So part of our goal was to be able to use these data to correct them from their, to account for the site condition in the evaluation of the distant California data, but also to deal with kappa from the local earthquakes. And so if we're using any of these here for kappas, we're going to be getting kappa from soil sites. So the summary of what Rob did is he found of the 11 sites, 2 were rock sites. 113A was the site that we had studied. This site was actually a bonus site that he provided to us. That was not the right place, but it ended up being a site that was a rock site, so it's good. We had not previously characterized the ground motion for that site. We now want to go back and look at those ground motion data because we're so sparse on having rock site data. The velocities here, VS30 is in around the 1,000 meters per second range. 9 of the 11 sites were soil sites, so 380 to 640 meters per second without a soil depth constraint. So that leaves us to a problem of not having good ways of controlling the deep amplification and the total effect of the soil on the kappa value. But this is important for us to have this characterized so we know what the site conditions are there. So then I'm going to talk about the record processing. This was done by Pierre as well. How the Hero has been leading this with work at Pacific Earthquake Engineering and analysis as well. So these are the 15 sites that they used for collecting the ground motions. Not all of these are ones that we had characterized. We characterized the sites in this range here for our kappa studies. Okay, the events here, these are the earthquakes in California. These are earthquakes in Arizona that were recorded at that array of stations. When you put that all together in magnitude and distance, we have here a bunch of smaller magnitude data recorded close in. So these are our Arizona sources. This is mainly used for kappa studies. And then we have our more distant data here, larger magnitudes that are used to evaluate the ground motion scaling, the path effects as we go from California sources to Arizona. So, and they had done an initial comparison from Elmira Kukapa of all the data in NGA West 2, plus then these are the sites at peak acceleration from the Arizona data set, and these were the sites over here from the at the period of 1 second. Going into this, we had been we had the preconceived idea that if the Q values are higher in Arizona, we would be seeing less attenuation, and if anything, we were expecting the Arizona data to show up higher than what the California data were. That's not the case, and we'll go through it moving forward with some other data comparisons, but the data overall from Arizona looked to be compatible with the California attenuation as opposed to being shifted high to account for the higher Q values. So this is an important case where we can now use data to calibrate ourselves as opposed to just pushing the analytical model. So there's a flat file that's been put together, and the data are all available currently on the Pierre website. This full data set, Yusuf's nodding his head, so I'm happy. That's good. So Pierre did a good job for us getting all this stuff out in time and before this workshop. And all that stuff's publicly available and can be downloaded. So with that, we're able to now use those data to evaluate the scaling. So I'll show you an initial evaluation that was done by Jenny Watson-Lamprey on the scaling of the path effects from California sources. These were the earthquakes, and so over here, these have an NGA West 2 earthquake ID. That means those earthquakes were available to the ground motion developers to use in their models without the Arizona data being in there because they had not been included yet. So The magnitudes you can see again are mostly in the magnitude 4 range, and we have the biggest one being Elmira-Kukapa up here at 7.2. So this is going to let us then use the models or compare the data from California to Arizona for these events. So there's several pictures here that Jenny had put together, but this is the stars are these crosses here are the recording sites. The circles on this side are going to be earthquakes. So we have earthquakes up in the northern range, sort of in the middle here, and then in the southern end. And I'll show you a few examples of what the attenuation is from those different regions. So starting in the north, this is one of the earthquakes. These plots have 0.2 seconds here, half a second in the upper right, 1 second in the lower left, and 2 seconds in the lower right. So with those, you can see here that we've got the red data are the Arizona data that we've added in, and the blue data here are the data that were already in, blue squares, already in the NGA West 2 data set. Okay, so the models were fit, in this case the Cho and Young's model, to the blue points. Different subsets of those blue points may have been selected by different developers, but the key point here is that when we're looking at the red points, they look at an extension or are consistent with the blue data. They don't look like there's a shift and that there's something fundamentally different going on. That's a magnitude 3.4. Here's a magnitude 5.1, a little bigger, but we just have a few data points here at the end. And the key is they don't separate themselves out as a separate population. From the middle, so you did the same thing looking at some of these events coming across. And I'll just show again 2 of them. So here's earthquake 4.5 magnitude, and we're seeing the ground motions from Arizona are consistent. I should say these points have all been corrected for their VS30 so that they have a common VS30 value. So we've removed those effects. In these particular plots, they've also been adjusted by the Cho and Young's event term. But our key comparison is not really with the GMPE, but it's really the blue points versus the red points here. And this is another one, magnitude 4.3. So here, the model is over-predicting, but you can see it's going similar over-prediction for both blue and on the red points. The last zone she looked at was from the south as it comes across. This is our big event, Elmira-Kukapa. So the red points here, you can see, again, are consistent with the blue data points. So our last one would be a smaller one. This is one that actually had more differences. For example, right up in here for this 4.6. This was sort of the effect we had initially envisioned of a higher short period ground motions due to higher Q values in Arizona. But that's really the only event where we can see that feature showing up in a consistent way. So when we went through all this, Jenny's conclusion of this, no significant difference between the data that we're seeing in the distance attenuation from our generic California models and what's going on in Arizona. So her position is you would not need to change the model for application to Arizona. We also had some discussion about this. So again, Q differences are not large enough to affect the attenuation as ground motions propagate from California to Arizona. So part of this is we're getting the what's happening in California and any propagation effects there, but there's not enough path in a high Q environment to make up the difference. Questions we came up with, is there a regional source effect? Are there differences in the source terms between earthquakes recorded in one region down here versus another region? And there's reasons to expect that. If this is an area of higher attenuation or heat flow, are we having really lower stress drops, if you want to think about that, or higher attenuation right in the source region? So we'll look at those event terms. And that will be shown tomorrow afternoon. Then we're going to be updating those comparison plots as well to add all of the GMPEs and adjust them by the event terms rather than adjusting the data. For the comparisons I showed you, that's not a key factor. And then there was other cases where sometimes it looked like the median didn't go through the center of the data, and we're trying to understand why. It depends on the subset that's selected is part of it. Not all of the ground motion models use all of the data, and when you only have a small number, which is what those typically are, some of the event term is partitioned into some of the residual goes into event terms and some goes into within event residuals. So there is when we look at these things, the bottom line is smaller numbers of samples means your model, your optimum model may not go through the center of the data in those cases. All right, so let me run through kappa, and then we'll see if you have any questions on all of the Arizona data and analysis together. So Olga did kappa estimates for us, and I presented that for her at the January meeting. The data to estimate kappa are just those local data that we talked about. So that's the little earthquakes, magnitude 1 to 3.5. And this is the distance range here. Depending on the magnitude, it's going to control where you are in the source spectrum, and so how you can measure kappa, which side of the corner frequency we're on. Are we above or below the corner frequency? So these are ones where we can measure the kappa using the acceleration spectrum. So the corner frequency is low enough that we can look at the slope of the Fourier spectrum above the corner frequency. These have to be looking at displacement spectra. The corner frequencies and magnitude 1.5 are going to be outside our frequency range. The Arizona data here are from the TA array, meaning that their highest frequency, their Nyquist is at 20 hertz, and their highest usable frequency is really 16 hertz. So when we're down here, we're going to have corner frequencies above 16 hertz, and so we need to do something else. So she's looked at the slope and the displacement spectrum. In the middle, we're going to use kind of both methods, assuming either it was a really high stress drop or a really low stress drop, which lets you try to use the acceleration spectrum either down further or the displacement spectrum up a little bit higher, and I'll show you what we mean by that. So depending on what you're trying to do, if you had a 50-bar stress drop or a 1-bar stress drop, the correlation of magnitude versus corner frequency, and this is our usable frequency band to work with, okay, up to 16 hertz. That's all that we have to work with. So based on these, if you're at 1 bar, then you're going to have lower corner frequencies, and you can try to use the acceleration spectrum approach. If you're at 50 bars, then you're going to be way up here, and we're going to be running out of space, right, to work with, and so we'll have to be not able to if we're up at high enough frequencies, the corner frequency is too high, and then we're going to have to use a displacement spectrum approach. I'm sorry. Other issues we have here are that we have potential side effects. So what Olga did at this point was measure kappa as a slope on the Fourier spectrum without correcting for side effects. Okay? And here's just an example of the perils of doing that. So what she looked at is one of the stations here, Y15A, and looked at the H over V ratios, which can be an indicator of site response or side effects. And the H over V has a peak in the central range here. So if you're trying to measure kappa in this frequency band, 6 to 16 hertz, and you're going right through a site resonance, it becomes problematic to try to do it. You can try to then avoid the site resonance and get over here, but now you're running out of bandwidth to work with. So I think a summary of Olga's work is it's really hard to work with this data. The data are not ideal for trying to estimate kappa from these stations. A lot is due to the limited bandwidth that we have from the TA array data. So given that, moving forward, there will be updates on the kappa, taking out the side effects to the extent that we can. But what I'll show you are kappa values with the side effects left in there. So, and I'm just going to jump to her model of kappa. The points are shown in here, and she has points using a displacement spectrum approach and points using the acceleration spectrum. The squares are the average of the kappa values of the range of values that she's got. And then we said we need a model, so she built a model for us. This is the dashed line here coming through. She used the constant in the first 70 kilometers or so. Then what's shown here are the implications of different, the slopes of this and what it would imply for different Q values from 500 meters per second to, I should be using the pointer, 1,200 meters per second. Okay. And her value would be, if she just believed this slope, it would be a range of around 900 Q value. The kappa value then at short distance is ranging from around 0.1 to 0.01 to 0.032. And this is our kappa uncertainty. What's important here is going to be the hard, if we look at the hard sites though, and look at our kappa value as a function, the residuals of that model versus the shear wave velocity. So most of the data, remember, were soil sites. And so she's fitting that on average here. Our one rock site is out here. So with this model, the one rock site has a kappa value that's not consistent with that model, right? So there's a large negative residual there for the kappa. This is at the kappa at distance, so that's not the uncertainty in kappa 0, but what's happening out at these larger distances. So the difficult, in summary of all of this, it's hard to get kappa. It's going to be a very uncertain estimate due to the limited frequency band, but this is the best that's currently available. We have one rock site, Y14, that we've been using. And note, as I said, Olga didn't remove the site amplification, so that's still there, and that we're going to need to remove it if we want to use the soil site. So for the rock site, we can use the kappa directly. The soil profile we have from Rob Cahan's study constrains the shallow part of the profile for us, but we don't know the deep part. And if we want to take out the effects of kappa onto the soil, you need to know the depth of it so we can get the total effective damping of the soil column. We may be able to use H over V ratios to get the soil thickness. There's also some generic maps of soil thickness that could be used to get at that. The recommendations or discussion at that meeting was really to focus on the rock site kappa, which is one number or one value, and that we should be going to the other rock site that we have and collect the ground motion data for that and characterize it. So we've asked Pierre to do that and adding another set of earthquakes or recordings just from that one station to the data set, and we're looking at getting that done in the next couple of months here. But that hasn't been done as part of the data set that's released, and that's correct, right? Yeah. Okay. Arizona, before I move on, any questions or comments about these Arizona data and what was done? Adrian.
When Rob was processing the SESW data, he shows both dispersion coefficient of variance and the inversion coefficient of variance. Did he correlate those two to get the total coefficient of variation?
He combined them, and I'm not sure what he means by combined. I don't know if anyone else here knows exactly what he did, but he did both. You're right. Different methods had different covariances, and he showed what he called a combined covariance.
I'm not sure those are not correlated.
They might be correlated, and so I don't know. That's why I need to be careful about what I know and I don't know. I don't know how he did that part of it, so we can check with Rob on that. Youssef.
What is the VS30 at the Arizona site nuclear plant? Remind me.
I'm trying to remember that. Do you remember, Bob? It's got soil, and is Melanie here? Melanie, do you remember what that is? You need a microphone if you've got that. It's a soil over a harder rock. Okay.
So I want to get the feeling because Olga had You said about 900?
Deep, yeah, but I think they're deeper profiles than the Palo Verde.
Okay.
It's between, I think, I'm not exactly sure, but between 1,200 and 2,200 meters.
That's the rock, but it's a little lower in the soil part. So, Yusuf, we have that from a couple years ago presentation. I'll pull that up and we'll cover that when we talk about Arizona tomorrow. I'll be sure to have that one for you. Any other questions? Steve?
Just to refresh my memory.
Could you need to get that closer to your mouth?
Yeah, to refresh my memory, is it correct that the models will only use kappa naught, or do they use kappa of R?
Just kappa naught. So for us, this is the kappa that goes into the point source stochastic model, which is a kappa naught, and then Q comes in as a separate term. So the kappa at distance is a combination of those two things. So kappa is tricky in terms of we use that word for a lot of different things, but we're talking about really this number here being the kappa at zero distance or short distances. If I could make it, I can, in this region here. So that's, I guess if we say without anything else, that's the kappa that we're after. And we're using these data at larger distances to help us try to extrapolate back to short distances. This is all a plug for you to write to the TA array people and tell them to crank up the sample rates to 200 samples a second, not. So Christine says the permanent stations will be having a higher sample rate. 200 samples a second. So happy days. That's good for us in the next round. Any other questions on the Arizona data? Okay.
Just one question for clarification, Norm. So you will provide the kappa for the rock in Arizona, because that's
Yes.
what we need as input to the site response.
Yeah, so that's part of, so it's not part of our GMPE, but it's part of our handoff. So we have to give you the kappa and its uncertainty. Okay.
Okay.
So, and that's we are going to treat that as part of the site response.
Okay. Will you also provide a VS kappa adjustment from 760?
I think the answer is no, other than to say it needs to be done, because it depends who's, the reason I say that is it depends who's running the site response. Sometimes they want it, sometimes they're going to do it themselves. Okay. So we're going to say, well, our reference is 760. Here's how you could correct it to a generic number at a different velocity. Let's say it was 1100. So we'll give them the methodology, but we're leaving the implementation to the site response part because it's still not clear to me exactly what site response method each plant will use. Okay. But yet, in the end, there has to be unambiguous rules on how this is done.
Exactly. Then, Norm, that also, I wanted to bring it up previously. So it needs really a strong interaction between this group and the site response.
Yeah, it has to be.
Otherwise, it's going to go crooked.
Right, it has to be fully integrated. And so we're trying to get our group here to focus on how things scale with magnitude and distance and hanging wall effects and so forth, and bringing the kappa, we get the estimates the best we can and bring them into integrate them in the site response part. Other questions? John, you're just stretching, is that right? Okay. Okay, next topic was hanging wall effects for small magnitudes. The background behind this is that the GMPEs have different assumptions about how hanging wall effects scale with magnitude as you go down from magnitude 6.5 down to 5.5 and so forth. At some point, they go away. They should be 0. Okay, being the earthquake is small enough, there is no more hanging wall effect. The models, there are different approaches, but they tend, two of the models are attenuating the effect by magnitude 5.5. I think the Cho and Young's model still has the hanging wall effect showing up at smaller magnitudes. When we've used, our empirical data overall has been really inadequate to capture how hanging wall effects scale with magnitude and distance and dip and depth and all those types of things. We have just simply not enough data, and we've relied on numerical simulations to control those, that scaling. But those have been done for larger magnitudes, and we are left with the question, how do we work or estimate the effects for smaller magnitudes? When does it go to 0? So to do that, we needed to then use the models from the simulations and have them look at them for smaller magnitudes. And before we did that, the question is, do they work for smaller magnitudes? These simulation methods were geared towards breaking up a big earthquake into small pieces, and we wanted to be sure that they were valid for smaller events. So SCEC did an additional validation for us for magnitude 5.5. This is called a Part B validation. So if you sat through this, this means it's a check of the simulation method against the GMPEs where they are adequately constrained. So 5.5 at 20 and 50 kilometers away. Right. So again here, I borrowed these slides, and some of these people put in animation, which I don't do, so that's why I struggle a little bit. Okay, this is the, we wanted to run generic ground motions from, against recorded ground motions from California and Japan. That's Part A, but we're just looking here at Part B, validations against generic GMPEs. So we're going to do validation cases before. We had done them for 6 and these sizes of earthquakes in this range, which were well constrained. Now we're going to push this down to smaller magnitudes. Okay, so we're going to do a magnitude 5.5 scenario, dipping 45 degrees, top of rupture 6 kilometers with Leonard scaling relation. Okay, and 50 realizations for each source, and 2 crustal models, and lots of stations. And I'm not going to show you all the details. I'm going to jump to the answer. And wow, something happened on our grids. That checkered pattern is a log grid behind there. If you squint your eyes, that's what you will see. So if you remember on the Part B validation, so you have to remember this back from our workshop 2, we had a target range and then a range of allowable models, and that's shown by the dashed lines. The simulations then have a data point. The red point is their average value, and then we have box plots showing you the range of the values. On the left-hand column is XSIM, the center is Grayson-Petarka, and the right is SDSU. Our criteria for passing the validation is that in the period range up to 3 seconds, these should be falling within those dashed lines. Okay, so we just kind of have a pass, no pass grading scheme here. And you can see the first 2 for this case are within the range. The SDSU is just barely popping out, but it's right around the top part of the range. If we go to 50 kilometers, it's a similar issue here. And you can see again now the models are beginning to be closer here, coming outside the range a little bit. There's a center line here, this solid black line, which is left over from before, so you shouldn't pay attention to that. Just for reference, that's the average of the NGA West 1 models. They systematically over-predicted the smaller magnitude events, and we know that, so that it's not in the center where the NGA West 2 models are. So from this, the basic conclusion was Grayson-Petarka and XSIM would pass our Part B validation for a magnitude 5.5 earthquake. SDSU needs a little revision. It's simple, though, and that it's a parameter change, and that we don't have to redo anything with the code. It's just an input parameter change. And so we are, Kim Olson is to provide us with rules on how that parameter changes with magnitude. Have we got those from you yet, Kim? Yeah, so we have those rules, so thank you. So with that, we're able to use the simulations and start to run them for smaller magnitudes. So then we can see what's been done. So this is from Doug Drager's presentation at that last meeting. And again, summarizing, before we had magnitude 6 and larger from the numerical simulations, and now we're going to go down to magnitude 5.5. And I'll just jump again to the summary of the results here. So what's shown is hanging wall scaling, or what the ground motion is on the left-hand side for magnitude 5.5 at the top, 6 and 6.5. These two are at a z-tor of 2.5 kilometers. And so when we start to look at these, if what we're seeing is the hanging wall effect, I'm going to use the pointer here, we get a skewed or pushing over of the distribution, widening out over the rupture, over the hanging wall side. And so when that's happening, and you can see it's bigger here, broaden out more for larger magnitudes, you can also see what's happening on the hanging wall side here by putting a straight line across, so you have a good reference point. This increase that we see comparing the footwall side to the hanging wall side is telling us about the hanging wall effect. And the bottom line is we still see a hanging wall effect even at magnitude 5.5. Whereas we had assumed in our ground motion models, or at least I had in mine and others, that would go away by that magnitude. Okay, so we're going to have to do something about it. So Doug Drager also went through and looked at some analytical explanations that we were thinking, does radiation patterns start to play an effect, as well as geometrical spreading. Previously, we thought of hanging wall effect as mainly a geometrical effect. When you're on the hanging wall, you have more of the rupture close to you than when you're on the footwall side at the same rupture distance away. So the point of all this is they're analytical models that you can look at to explain why the hanging wall effect should be still seen at smaller magnitudes. And the key of all this is that Doug summarized. He went through this in detail. There's two bumps in the hanging wall terms that you saw, and he sees those being related to radiation pattern. Okay, and we also then have hanging wall effect related to the dip and the top of rupture. The relative amplitudes appear to be here dependent on magnitude, so they become larger at the larger magnitudes, but still not zero at the when we go to the small magnitudes. When we look at this whole effect, comparing our GMPEs with the simulations at magnitude 5.5, so this is kind of our bottom line thing here, that the simulations are producing a hanging wall factor here bigger than what's in our GMPEs for this size event. Okay, so the bottom line is this difference is not incorporated in the ground motion models, and but it is showing up in the simulation. So what are we going to do about that? Okay. So from the hanging wall discussion here, we are expecting that the ground motion models that were tapered to have no hanging wall scaling at 5.5 probably need to be revised in terms of how they behave in that magnitude range. Okay? So all of the simulations show some hanging wall effect in the short period range at magnitude 5.5. And the results here are similar, indicating it's the geometry, because XM really is only a geometrical model. That's the main thing it has. It doesn't pick up radiation patterns. Okay, so how are we going to adjust the taper? For two of the models that have hanging walls, Campbell, Besorgnia, and the ASP models have explicit magnitude tapers, so those are kind of easy to go and modify. We can just adjust them to leave it as a higher, tapering out more slowly with magnitude. The Cho and Young's model is going to be a little more difficult for us on how to do that, but it also may need less adjustment. It had a higher hanging wall factor than our other models. If I start to go back, Cho and Young is this one you see here, and it's staying higher on the hanging wall side for these smaller magnitude events. So it's doing a little better job. Okay, any questions, discussions on hanging wall? We're going to have to do something about how the models behave for smaller magnitudes. We can't use them simply as published. Ken?
It seemed from those, when you drew that horizontal line, that the hanging wall effect was actually being observed, at least in the simulations, out to 20 kilometers or so. I think we do have data there. Have you compared the
be careful
simulations with the data?
I went through this about that. Remember, what's on the x-axis here is not rupture distance, it's Rx. So these points at 10 here and 10 here are not at the same rupture distance away.
Well, for a small earthquake, it's
it's
that different. Okay.
Correct. It's closer to being the same.
So it's just an observation here, and the question is, have you looked at the data? Maybe right now you're just assuming the simulations are correct. You're going to correct the models, but it seems to me there is some data at least out at those Rx distances.
Well, we'll show later what we saw from Japan. There's surprisingly not a lot to use on the hanging wall side. Doug?
I was just going to add, if you compare on the right, this is for a 45-degree dip. The top is 5.5, and then the middle is 6. And for 6 and 6.5, which are the two bottom panels, you really do see that effect, but it's much less pronounced at the top panel. The top panel for magnitude 5.5.
So what Doug is, if I summarize, saying that here the difference between this line to there is larger for the 6.5 than it is for the 5.5. So we know it is getting smaller, but it is not as small as we had assumed that by this time, 5.5, you think, geez, you're almost to a small enough source that we could ignore these effects. So there is still something here. So this is important for us because we're going to be, for Diablo Canyon, we're going to be dealing with reverse faults in this range here on the hanging wall side and in this magnitude range. So we need to be able to capture those appropriately for their hanging wall scale. Other comments? Ralph?
It's not surprising that at 0.2 seconds, which would be at 5 hertz, that the three methods would agree, because the other two methods randomize the radiation pattern. So the radiation pattern that Doug so nicely illustrated would not show up in that particular example.
Right, and I really condensed Doug's presentation dramatically. He was focusing on the radiation pattern on the longer period parts of the evaluation. Here, our main interest in hanging wall effects is at the shortest period, because empirically that's where it's the strongest. But you're right. You could say if you randomize a radiation pattern, then they all have the same geometrical effects in them. Other questions or comments? No. Okay. Let me move on to. How did I get there? I'm going the wrong way. Okay, upper tails. So I don't. There would have been a. Tom Heaton had said we should be looking at the distribution of the tails, and the same issue with what John Anderson has said, looking at very large events, and they can happen, and that's the part of the distribution we really care about. Right? So hazards are going to be driven by tails, and a really rare events that we're after for capturing here for nuclear power plants is really pushing along the tails of the distribution. So what I had shown, for those of you on the phone, there's rumbling going past. I'm just going to wait a second until they're gone. Okay. So these are normal probability plots from the ASK model for the within event residual. So on a normal probability plot, we have the expected quantile on the x-axis and the observed quantile on the y-axis. This is a normal probability plot here. We're interested in the upper tail. We really don't care about what's happening on the lower tail. And so if this thing deviates above the line, that means the tails of the distribution are fat. Okay, so in a really simple way, if I drew my distribution and made it going out fatter than what log normal would produce, then it would be above the line. If it was below the line, it would be narrower or a truncated distribution. So these data are showing us here, and this is around 3 standard deviations. It's pretty good, but beyond that, we're getting fat tails. Okay, and the left-hand side is the PGA, and the right-hand side is 1 second. We also looked at this, what if we just use bigger magnitudes within 30 kilometers? And because the previous one had lots of large distant events, and maybe that's what you're looking at. And here the tails are still getting fat. We have less data, so we don't go as far out along the edge of the tails. Okay. So the implication here, and so this is now the between event part, so this goes into the tau term. We have now 1 point for every earthquake, so there's a lot fewer data points than what you have when you have 1 point for each recording. And we see no deviation from log normal here in our event terms. We also had looked at the simulations to see what are they showing. This was the forward simulations from the Grayson-Petarka method for the Lander station. 50 realizations, so I'm only going to get out to just not quite 2 sigma, right, for 1 out of 50. This is 3 seconds and 5 seconds. We focused on this because that's the part where there's randomization in the slip model, and that should be affecting the distribution of ground motion. And here we can see we don't have enough data to tell us there's a deviation from log normal from this distribution. Okay. As I'll mention before, in just a minute, the simulations, while we're checking them here, have not yet been validated for variability. So this is sort of a check of what's coming out, but we haven't calibrated them yet to say we've got the right variability. So the summary of all this is when we're looking at the log normal distribution and its applicability, we care about the upper tail. Okay, we may deviate in the lower part of the tail. Hazard doesn't care what's happening below the median. Anything below 0 is not affected to us. We care about exceedances. The distribution of the residuals from the ASK model shows that we do have a consistent with log normal up to 3 epsilons, but once you're beyond that, you're getting fat tails. Okay, and that still works. There's a way we can model that using a mixture model, and you'll see a presentation later on tomorrow, I believe, on mixture models. That's just simply saying we're going to make a model combining 2 normal distributions to broaden out the tail. And we'll show how that works. Still have a few points above the threshold, so it remains uncertain, but there's an indication that there are broad tails. The between event residuals in some cases have skinnier tails. Whether they're skinnier or not really is probably not well constrained, and I think we won't be trying to model that part. The small set, the validations was a smaller set, but really I'll put at the bottom, that hasn't been, they've been validated for medians, not yet validated for variability. That's a longer term effort. So we will be trying to validate the numerical simulations for variability in the next few years. That's not going to happen in the time frame of the Swiss project. Questions on distribution? You'll get to see a little more of this on tomorrow. We've also right now been looking at the distribution of the ergodic assumption models. And the question then is, would we have that same kind of a tail if we were using the station-corrected values? Because maybe our tail is coming from the same station popping up, or is it really coming from variability in the past terms?
Norton, just one observation. I would think you'd need a whole lot more distributions than just the few from Landers or something like that, before you could come to some systematic understanding about about those fat tails. It seems that just a very few observations wouldn't be enough just because of variability.
Sure. So we have uncertainty, right? That few observations means higher uncertainty for us.
That's epistemic uncertainty.
It's epistemic, and so now we will have 2 models of the tail. One is it stays log normal, and the other is it goes fat. Okay.
Right. And I was saying that the data, they're not data, but the data would peak if you had enough of them. And without them, it's just really going to be indeterminate almost.
Yeah, so if we had enough data, it would be a straightforward problem. I fully agree with that.
Of course.
So we don't have enough, but the data that we do gives us an indication of a fat tail right now, and so we can't ignore that. We need to capture it.
No, for sure. You absolutely can't ignore it, but pinning it down is harder.
Yeah, pinning it down is difficult, so there will be still high uncertainty in what this part of the distribution looks like. Fortunately, it's showing up beyond 2 epsilons, right, and really beyond 3 in most of these cases, in some of the cases. So now that part is not driving our hazard in the 10 to the minus 4, 10 to the minus 5 range. There our epsilons will be driven 1 to 2 typically are going to control that number. When we're going to the higher parts, 10 to the minus 6, 10 to the minus 7, then these will be an important contributor to that. You said.
Is it at high, is it at all frequencies? What did I missed the frequencies?
Yeah, so we see the fat tail at several, not just one frequency.
Okay.
Yeah. Ralph.
Just to comment that Danielle Lavallee and I published a paper on the Chi-Chi earthquake on the main shock, and we actually showed that the PGA definitely had a fat tail. And this was at distance, at the close distance of 0 to 10 and actually out to 30 kilometers, that it was always a very fat tail in the PGA. So this was a paper published in 2005 on the Chi-Chi earthquake, which I know is a big contributor to the
It's in here, correct. If there's a difference, the only thing would be that we have corrections for hanging wall, we have corrections for site and all of that in there. So, but we can double check or compare with your result. But if anything is fat, it's clearly not going to a skinnier tail.
Norm, one question. Is that fat tail showing up at all magnitudes? Do we know?
So, no. So we've done this. I actually had shown last time one at magnitude 6, but now you're running less and less data, right, as you start to run that. I'll pull that up later, but so here the point is, if I go just to big magnitudes, I don't have enough data to work with. But we are seeing this still, this tendency, even when I did 6 and larger, it was still towards a fat tail. So it didn't go away. It's not driven by the magnitude 5 to 6.
Okay. The other thing is, it's way within the KS bounds, but that doesn't mean it doesn't exist.
Correct. See, that's what Bob was getting at. He's saying this is all, you could, what have I done? You could tell me, I could say this is all statistically insignificant. That's not our charge to say whether it's significant or not. I need to say it could be there, right?
So these asymmetric high frequencies that we see are a real phenomenon, and they are clearly only show up when you get a very large record. Typically on the vertical, they're -1 G, and then anything on the positive side.
Could you put the mic a little closer?
-1 G on the negative side, anything on the positive side, and -1 G, they can't be a coincidence. So, and when we think of it, it's got to be some sort of nonlinear phenomenon that happens around 1 G vertical. And then we're trying to characterize statistically that positive side of the curve. And it'd almost be surprising if it would turn out to be some sort of log normal distribution when we are clearly going into some different kind of physical phenomenon. We're mixing one kind of phenomenon, then we move to a range of something different. And I don't know how to deal with it, but probably the easiest way, we talked about it a little bit, the easiest way is for the mechanical engineer to add some sort of bearings or bushings in the system.
Bob, did you have something else you wanted to add, or just about, I saw you reaching for the microphone there. No. So I think part of what we're talking about here is what's robust statistics and what do we put in, okay? And non-robust statistics doesn't mean no uncertainty, right? That means we need to track what the allowable range is. So you could say this range, the error bars are broad enough, I could have skinny tails or I could have fat tails. The small amount of data that we have is biased towards the fat tail. That's about all that we can say. But within the statistical uncertainty that I would say, I don't have high confidence that that's the correct model. Okay, I need to finish up. So let me run through the last piece, complex ruptures. So this was presented by Katie and Jeff Bayless. And complex ruptures are ruptures where we have a change in, I should show it from here going to there, change in strike, excuse me, not strike, change in rake and dip along strike, and I'm going to just jump to the end. So the bottom line is our GMPEs, we have to put in a single number. We have to put in a rake, style of faulting factor, and we have to put in a dip for the hanging wall effect. And we have to put in a width as well. Okay? So, so what do we stick in when we have differences? So I have a strike slip part of the rupture and I have a reverse part of the rupture. I need to choose. So we have to choose those values. So the way we did this is looking at 4 different ways of sticking the values in. One, treating the 2 pieces as separate earthquakes, estimating the ground motion for each one, and then SRSSing them together, basically saying they're going to have random interference. They're going to arrive at the same time, and we're just going to use RVT to get a single value. The other one we'd say, take a single fault with the full magnitude of the combined pieces, and then weight the average parameters, rake and dip, by the area. So how much of the fault area is strike slip, how much of the fault area is reverse, and then plug those points in, and you plug in the distance to the closest point. The other methods, you're going to hear about these again later today, is doing the same thing but weighting those average parameters by 1 over the distance squared, or we could be using just simply the parameters associated with the closest segment. So if I'm closest to the reverse segment, that's what I use. If I'm closest to the strike slip segment, that's what I use. We also have simulations, and we're assuming they give us the right answer. Okay, and so we're going to look at these 4 different simplified methods and choose the one that gives us the closest thing to what the numerical simulations say would happen. And I'm going to jump ahead to try to get the answer for us here. Katie, I have your problem of I have to PDF it. Yeah, that's not good. So these are coming onto their side. So we had a case with a Hosgry fault and then breaking to a Lososos. So it would be a strike slip fault, continuing on to a reverse fault. It's dipping back this way. The plant side is here on the hanging wall. Now what parameters do you put into the GMPE? So I'm not going to be able to tell you other than, are they all like that? Yeah. I'm going to jump to the end. Katie will show you this. Why don't you pull up the your PDF of these 2 plots, and she can show those when she gets there. The bottom line is we compared those 4 methods. The SRSSing works the best. So it is closest to what you would get from doing a numerical simulation. Okay? For our approach right now, we're planning to use a single rule, that is without any epistemic uncertainty. So our rule would be SRSS the values. Okay? We're going to, because we think that this is going to be a small contributor to the hazard, because the rates of occurrence are so small compared to the rates of the faults rupturing separately. But we'll check this assumption when we see the draft SSC model that should be available to us in April. If it becomes a significant contributor to the uncertainty, then we need to go back and address the uncertainty in that parameter instead of just adopting a single rule. But right now, we're going with the single rule of SRSSing the results. The bottom line is that looks more similar to what the simulations produce than the other methods of trying to choose some average value along strike. Questions?
SRS is independent of the distance of the station to fault?
If you SRSS them, so if this was my case here, I would take the distance from the station to the this part, treat it as a separate earthquake. Then I get the distance from my site to the strike slip part. Okay? So it's like the two separate earthquakes. We're going to compute the ground motion from each of them, and we're assuming that they interfere in time so that the strong shaking is overlapping from those two parts of the rupture. Okay, and so then we can use RVT and SRSSing it. That's not, and so when they did the simulations, they did a simulation for this piece, a simulation then for the strike slip part, the simulation for the reverse part, and then added them together in the time domain. Okay, and SRSSing is similar to that. It's not surprising that that works because it's the same basic concept that we're adding in the time domain where they're overlapping with their strong shaking. So this is an easy rule that we can use in the hazard calculation. It's easy to Melanie and to Nick. I don't have to do that. They have to do that. If no other questions?
So Norm, in that rule, are you using the magnitude of the combined or the magnitude?
No. Magnitude of the separate ones. Okay. It's like two earthquakes. Double event, we're going to call it.
So it seems like it would only work as long as the ground motion amplitudes are roughly similar. I mean, if you know, I think you're getting a bigger magnitude on the strike slip one probably than the other one, and so even though the distance is greater, the amplitude may be greater. It just seems there could be at some point where that's not going to work.
But let's say we took Denali, where we're near the strike slip part for pump station 10, and then I go, hundreds of kilometers away to the reverse part. That reverse part will be so close to zero that when I SRSS it, I just get the strike slip part back. So I don't think it breaks down. The place that we're most worried at not working is this case where you're close to the two pieces.
Okay. Yeah. You're okay. Yeah.
So I think because of the distance, it's going to knock that other one down because it's far away. Yeah.
Right. So the single. Okay.
Right. You'll hear some more about this.
I hadn't really thought out my question.
Okay, that's fine. Brian?
Norm, can you comment on whether this approach is consistent with how the GMPE is developed?
It's not. So the GMPEs were developed using, if we go back to this stuff, either method 4, which is what I did. Okay, in the ASP model, we used this one, or using method 2, which was the parameters averaged along strike, which is what the others did. So the flat file has this parameter listed when it says rake and it says dip, and width for the fault when we enter a single number. So it is inconsistent with the way the models were derived. However, there are very few cases in the models where this is an important consideration. So we started out, if you remember in workshop 1, looking for data that matched this case, and Paul Somerville looked this up for us as well. 1 or 2 around the world where this is really a significant effect. So while it is inconsistent with the way the models were derived, I don't think it's Bob said, not a big deal. It wouldn't have fundamentally changed your GMPE if you chose any of these methods because there's not enough data points. Tom.
Norm, the example you show of the Lososos and the Haswi rupturing together is an interesting scenario because those two faults do not intercept in the subsurface. So about the only way you could get them going together is if the Haswi or one triggered the other, in which case they may actually rupture simultaneously. So in this case, would method 1 really characterize this? Because you're really having two seismic sources contributing to the ground motion simultaneously.
That method 1 treats them like they're two seismic sources.
Not just being the closest, but simultaneous rupture. Okay.
Yeah, it treats them like two earthquakes that happen, but when you get the ground motion, it's at the same time. That's really what method 1 is saying. So we're in a broad conceptual way, method 1 is more consistent with they don't match up, right? It's just not a rupture bending, and it's jumping and, as you said, triggering another earthquake as opposed to being the same one. We have the problem, when is an earthquake 1 and when is it 2, right? That's a recurring definition issue for us. Okay, any other comments? Gabe.
Quick question. Does the SRSS work for long periods?
Long periods? Yeah. Katie, what period range did you guys check? Did you check long periods as well? Yes. I think the answer is yes.
Oh, I'm surprised. Because it shouldn't.
How long of a period? So,
well, 10 seconds. But maybe
10?
the case is because the magnitudes are so different, maybe one dominates, so it doesn't matter. But it's a little surprising. Anyway, good.
At 1 or 2 seconds, it still works.
Okay.
Okay. So I think you could say the concepts of RBT may be breaking down at 10 seconds because because the periods are so long, but that's not going to be a controlling source for us. So I think I will defer that to interesting science issue or statistical model, but not really relevant to our hazard calculation.
At 10 seconds, it's consistent with the simulations for the SRS.
So if the simulations are working right, which are just summing in the time domain, then the SRSS is still working at 10 seconds. So it's magic, the magic of SRSS. Okay, any other questions? If not, let's move on to who's up next. Sorry, I kept looking at Katie.